Swayam Prabha. Digital India. Educated India.
So let's get started. I'm going to share my presentation. Today, I have planned two presentations and we'll have a break in between for some problems. We will be discussing some short, small problems based on my first presentation. Um, yeah, probably we can just spend some 5-10 minutes as a break, for you to get the hang of the problems, how to solve it, and all that. But probably we may not have time to solve all the problems today in class. Okay, so we may not,
Yeah.
yeah, even if you're not going to complete it in the class today, you can always do it as a homework assignment and we can discuss it in the when we meet in person. Today's talk is going to be about water. We have looked at it, water as one, the impact, LCIA, when we are discussing about that, we looked at water as one of the impact which can be quantified across the life cycle of any product. Water consumption or water usage is one quantity which is also being an outcome, which is an outcome of LCA tools. But I feel that LCA, whatever be the tool which is currently available, there is not much of an importance given to water, although we know that it is very, very a resource which is getting depleted by the day always, although we call it as a renewable resource, right? So the quality and quantity is not becoming accessible, although it is there, right? So we want to give a little more attention to water in today's session. Um, and I've used one concept which was in Holland. It was brought up as a first, I think in the late 80s, the concept emerged, a water footprint concept. I will that kind of highlight the importance of water, similar to what we have been studying in the LCA and the materials lectures earlier. We talked about what goes into making a product, right, in terms of embodied energy, uh, and how we can extend that to when you draw the boundaries bigger and bigger for your LCA, you can kind of see how much of energy goes into making a product, right? We did that in the last session with me. Um, and similarly, all the other inputs. So today, the focus is going to be particularly in this concept. They've used the same principles to highlight the importance of water and what goes into making a product in terms of water. Okay, so let me. How many of you have heard about water footprint? Or I'm not able to see you all in my screen mode. You can raise your hand, Niranjan. The concept of water footprint, just like carbon footprint. Okay, so not many. So I will. It's interesting. It's important that all of you get this kind of a thought process. It's basically a thought process for us to think beyond. Ramanan has also raised his hand. Yeah. So this is. I'll in initial 20-30 minutes. I'll be talking about this. This is a presentation which is already available in a website called waterfootprint.org. So I'm just going to share it with you and we'll have a discussion around it. Okay. So if you apply the same concepts of embodied energy into water for any product, and the the water footprint of a product is all the water which is required to make that product available for us to use. So it is the entire, if you extend back into the supply chain, the materials, in the case of a product, it can be materials which are used, raw materials which are used in making the product and the manufacturing of the product. There is a lot of water consumption in every stage, right? The water footprint gets highlighted particularly in water intensive industries or products which are water intensive, and also particularly when it comes to a agricultural a product which has its raw materials from the agricultural input. It gets highlighted a lot. As we all know, even world over, agriculture is the biggest water consumer. In India, it's about 85% of our water goes into agriculture, and 10 to 10 percentage around that goes for industry, and then only 5% goes for the domestic consumption. So this the water footprint concept started off with the agro product, and then it was extended to other products. So you'll find a lot of examples with relation to agro-based products. Okay, so it is an entire product in the production chain, entire water used in the production chain. And as stated here, it is also it varies from place to place, right? It also varies from time to time, depending upon the processes used in different places. Okay, and as the technology advances, you will see a lot of change. So water footprint of a product is broken down is as three components: green water footprint, blue water footprint, and gray water footprint. So green refers to the volume of rainwater which is evaporated or incorporated into a product. Again, look at it from the agricultural point of view. Crops, okay, there can be crops which are rain-fed, crops which are irrigated. Okay, so these are mostly rain-fed crops. Uh, consume a lot of has a lot of a green water footprint. Blue water footprint, how much of water is used from irrigated sources of agricultural farmland, okay, surface or groundwater. Or if you're going to look at the manufacturing in the second step, when it is manufactured or when it is taken to an industry for process, there is a lot of water footprint associated in the production process. So that is also accounted in the blue water footprint. Gray water footprint is an outcome of the production process where there is a lot of pollution which is created, and we need to account for the polluted water. Okay, that is accounted in the gray water footprint. We look at a little more closely. Okay, and it's a cycle. So what blue and green goes into the consumption or the production of a product, and gray is the comes from the pollution. Okay, so I won't go too much into this. They've broken it down into multiple uh, the water balance in the catchment area. And some simple equations are used. This is in irrigation engineering. If you have taken that course sometime, you would have seen these kind of calculations. The evapotranspiration losses are the biggest in terms of water consumption during the growth phase of the crop. So we use those parameters assessed by the irrigation engineers or the agricultural engineers to estimate the crop water use, and it is normalized per ton of crop produced. Okay, so that is same with the irrigated water also. Crop water use is a summation of the blue and the green water if both are used, rain-fed and irrigation is used. Okay, and all you need to know is Penman-Monteith equation, the very famous equation for crop evapotranspiration, and then you multiply it by the number of the growth period. Over the growth period, how much is the total evapotranspiration requirement of the crop? Irrigation, there are ways to calculate how much irrigation is required during the crop's growth phase. And how do they calculate gray water footprint, which is more of our environmental engineering domain? So a simple calculation for gray water footprint is how polluted is your water and how much more water you need to add to dilute that pollution and bring it back to its original quality. Okay, that is the total gray water footprint of the product. Let's say your water went from 0 BOD to 100 BOD during your manufacturing process. Okay, then you need to add 100 times more water to dilute it so that it comes back to its original state. So that is the volume of water that is required to bring it back to its original state. Okay. Any doubts in this? These are concepts, okay, to highlight, as I told you, the importance of water and the water footprint of different products what we use. Extending this, we're looking at a cotton plant, right? So cotton plant uses, once it is, it incurs a lot of water footprint during its growth phase. And then when it goes into its functional phase, where it is probably converted either into a cotton seed oil and refined, or the seed goes into it and the lint goes into making garments. That's primary objective of growing cotton, right? So during the manufacturing of the garment, again, there is a lot of water consumption, the production phase. Okay, so there's a lot of wet processing, dyeing, finishing, and finally it comes out as a garment. It has a huge amount of water consumption and a lot of gray water pollution, right? Gray water footprint is huge in terms of textile industries because of the dyeing process and all that. Whereas in the agricultural side, before it even came here, there also it has incurred a gray water footprint. How do you know? Can you tell me? How can gray water footprint happen in an agricultural field?
Due to pesticides being used.
Right, there's pesticides, there can be fertilizers, right, which is again going to be polluting either the groundwater below or the runoff from the agricultural field is highly polluted. So we need to calculate how much of fresh water it has polluted or it has lost their quality because of this effluent discharge coming from the agricultural runoff. So we also have grey water in agricultural fields. So when people do all this math, okay, to find out how much is a water footprint of a t-shirt, a cotton t-shirt, considering that we have all these inputs given to us, the number which comes up is 2,700 liters for one t-shirt which is made of cotton. Right? That's huge. I don't know how many of you understand the impact of this. Right? So when we were discussing the LCA and circularity of fabrics or fashion, we call it, you know, the fashion industry is the biggest has the biggest consumption of energy and resources. Water is one thing which we don't look at very deeply, right? So these numbers were actually calculated to highlight that water impact, what impact on the water resources of products. Any questions? Bindu's daughter is also attending my talk, I think. So yeah, the same concept, when you go a little bigger, when you scale it up and think a little bigger, no, the systems thinking and how all these are related, when you look at the global context, right? A lot of cotton products are exported, particularly India is a big exporter of garments, particularly cotton. Tirupur, we talked about it earlier also in my first presentation, right? Similarly, there is a lot of export from other places, China, a lot of Asian countries, okay, and some African countries uh, are also. This is with respect to European Union, how much of an impact it has on the blue water resources of other countries. So here you can see the numbers there. So EU's impact on blue water resources by just consuming the cotton, okay, from the garment industry. Similarly, green water uh, consumption. These are like big numbers which is pulled out from the data from different countries. So there is a huge, there is the water footprint need not be within a geographical domain. Based on the imports and the exports and the trade happening, there is a carbon footprint of one country can come from or impact other countries. So that's a big uh, impact. We have to look at it, how the impact spreads across the globe. Right? This is just one example of cotton consumption, gray water for that matter. Again, India, depending upon how much of water pollution is happening, the quality of water which is getting impacted during the production of cotton products, they calculate the gray water footprint. And the impact of this, okay, on water systems has also been discussed in this particular website, waterfootprint.org. Two places where they have looked at the garment industry's impact is the Aral Sea and India's Ganges, river Ganges, where a lot of textile industry is located, or in Tamil Nadu, Noyal River is completely impacted by the textile industries of Tirupur. So there are huge impacts which are getting transferred, okay, from the point of consumption to the point of production. So several such examples are there for various products what we use in our day-to-day life. A cup of coffee, right? We never think about it. We have coffee every day, and most of the time people, the how much of water goes into our coffee. It's not just the 100 milliliters of water which from which the coffee is made, but the, the total calculated as per these calculations, blue, gray, and green water footprint, it is 140 liters for every cup of coffee. Tea is slightly less according to the calculations. Okay, so if you really want to be water conscious and you are okay with either tea or coffee, we should go with tea so that the impact on the water resources are a little less. Right? These can be used and interpreted in any way, making personal choices, okay, or countries can use these numbers to decide their exports and imports, okay, and industries can look at it from a different angle, how to reduce their carbon footprint, the manufacturing carbon footprint. The agricultural sector can look at it from how much water consumption, the blue and the gray water footprint, blue and green water footprint, how can they reduce? So these numbers can actually help people to realize their impact on water, focused on water. These are some fun things to show you so you know what is your water impact on your day-to-day product. Chocolate, there must be, all of us love chocolates, right? So 100 grams a chocolate bar consumes about 2,400 liters of water. Okay, something we probably did not think when we were eating chocolate. Sugar, again, a big water guzzler. Can you tell me how? What is the big, how did it come up to like 1,500 liters? Which will be the biggest water footprint? Blue, green, or gray? sugar?
Green water footprint.
Green water footprint.
Yeah.
Why?
During irrigation, it consumes a lot of water.
Yeah. Yes. So unfortunately, the agriculture is and the choice of the crop is decided in, I think globally this is the case. In India also it is the case. Sugarcane is considered as a cash crop in India. There are food crops and cash crops. Cash crops earn more returns. So people start growing sugarcane even in places where there is water scarcity. Water resources are not there, like Maharashtra, many parts of even Tamil Nadu, where we don't have enough surface water resources. People are drilling deeper and deeper to the groundwater resources so that they can grow more sugarcane. Sugarcane is a big water guzzler. It has a huge blue and green carbon footprint. Um, and mostly it's irrigated, so it's a huge green water carbon footprint. And simple things like tomato, you might not even have thought about it when you're cooking, using tomatoes for our cooking. So next time when you look at a tomato, I think this number should pop up in your mind, right? So it's 180 liters of water for 1 kg of tomato. Wine, 120 liters, right? But surprisingly, it is less than a cup of coffee, right? So you can, if you want to make a choice, I hope you don't decide based on this particular number to switch to wine for coffee, but something to think about. Okay, then moving on to like meat versus vegetables. Look at this big number for water footprint of a cow. So cow is like comes in the second, right? It's a producer, then it becomes a consumer in a food chain if you look at it. So lot of huge carbon footprint if, for beef comes from not only the cow's consumption, but like water consumption and servicing of the cow, but also from the huge amount of grains it is consuming over its lifetime to reach that stage where it can be sent for making beef. So that's the biggest. You see, 99% of the footprint comes from the produce which is used to feed the cow. Okay, it can include grains and also the hay and other things which the cow consume. Okay, so 200 kg if it of beef comes out of a cow, that incurs 3 million 100,000 liters of water. So this goes on and on. If you go to the website, you have the whole list of products for which you can come up with they are given water footprint of various products are given for you to look at. So that's huge. Even for 1 kg, it's about 15,000. So if you're looking at a hamburger with beef, 2,400 liters, which includes the bread and the beef and the small amount of veggies. Okay, so people have have compared the cow versus goat versus chicken. And like as we go down, the chicken has much lower water footprint compared to the cow per kg. On comparable basis of your denominator, it is still has a less water footprint compared to cow. Okay. And other products other than food, if you see paper, when you throw away a piece of paper, so far we were talking about embodied energy, which goes into the paper, manufacturing of the paper, the raw material and all that. But now we can add this number. Every sheet of paper has 10 liters of water associated with it. Right? So, and then this concept is also extended to different kind of biofuels, which again crop is the raw material. And so this is different types of crop which is currently being used as for biofuel. I think, yeah, sugar beet, more popular ones, um, rapeseed, paddy rice, cassava. I think Jatropa is something which I wanted to focus on. Jatropa, sometime back in India, Jatropa was promoted in a big way by the government for biodiesel production. Okay, I think now it's more importance is given to corn world over uh, for the ethanol and all that. So how much it may be great idea from the energy point of view because you're making fuel from a renewable resource, and it was all great. No, world over they celebrated all this. Even Jatropa was promoted and subsidized a lot by the Indian government, and farmers switched to Jatropa so they could make more money. But then these numbers tell a different story, right? Jatropa has the highest water footprint, and Jatropa again was grown in water starved areas, which had a huge impact on other needs of water by the local community. When the groundwater level goes down, open wells dry, and people suffer because some big farmer wanted to make money from growing Jatropa. So again comes in the social aspects of the choices we make as individuals and as a government. Okay, so these are things which we can think about and go back and look at other day-to-day things what we are using and what is our, just like how we did a carbon footprint calculation, a water footprint. How much of a water footprint does each person has? There are exercises which you can do in the same web page, and this was the outcome of one of the assessments done in UK. What is a water footprint? So your daily water footprint, like let us say a CPHEO in India, knows how much a person consumes, right? It is 135 liters per capita per day. In UK, it is probably 150, and in US, it is much higher. So that's all we think we are consuming, right? The government is supplying, or you have your own bore well and you're using it up. Okay, but having learned about this whole concept of your water footprint, they define the word hidden water footprint or the virtual water footprint, which you don't see. Okay, but there is blue water, gray water, and green water footprint in every product we are using apart from our direct consumption. So this 97% of the water footprint is the invisible water footprint, which is related to the products we buy in our supermarket, agricultural or industrial, from paper to your clothing, okay, to the car you use, same like carbon footprint, right? To the transportation you use, everything has a water footprint. And sometimes, like in the Western countries, if they look at it, most of their water footprint and the impact lies abroad, right? There is a lot of import of garments, pharmaceutical products from the Asian and African countries, which predominantly grows and manufactures uh, high water footprint products. So you can do a comparison between this is an interesting comparison between a meat versus vegetarian diet. We looked at it in terms of carbon footprint earlier, I think in Professor Su's presentation. But here you can see in terms of water, how much a meat eating person's water footprint is 3,600 compared to a vegetarian diet. So the impact, this largely because vegetarian diet also has a lot of water footprint from the agricultural side. Okay, so it is still much higher, the meat-eating ones, and in developing countries, it is not so much um, compared to the industrialized countries because it is homegrown. Most of it is there is no footprint which is coming from outside the country. So the same concepts have been used for national water footprint. We talked about individuals' water footprint. We can look at industries' water footprint when they are manufacturing goods, and the nation's water footprint. Okay, so the nation's water footprint is a much bigger concept where countries and trade can be decided based on this. It should be, but I'm not sure how much of thought goes into it when policies are made. Right? So a country has its own internal water footprint, which is inside the country, and then there is an external water footprint which it has in other countries if it is importing a lot of goods. Right? Similarly, when you are exporting, this is actually to look at consumption. There is a net consumption. You have to look at what is the water footprint within the nation, plus the water footprint which you are importing. And if you are exporting, you have to subtract the water footprint, virtual water which you are exporting, that is through your goods, right? It can be grains, it can be any other commodity like garments. Okay, so the framework, the National Water Use Accounting Framework, puts everything in perspective. So traditionally, uh, we just look at trade in terms of money, right? How much monetary gain you're getting. India is doing a lot of this textile industry and they're selling the products out. So there is a foreign exchange for the country. It is it's good for the country's economy. It's good for the industry's economy because there is a huge profit when they are exporting it. Okay, but have we thought about the water which we are exporting along with the product with which we have used a lot of this product, lot of this water? When you are exporting a product, so much of virtual water is being sent out of the country, right? So these are big decisions which needs to be thought about before we decide. And people, I think other countries are quite smart when they decide on what to export, what to import. Most of them, the water intensive production and so many countries are smart enough, even though if they have a lot of water resources, they try to import those kind of products from other countries, saving their water resources, right? It's just like mines, like in US, there is a lot of lithium, they say, are found in their country also, but they try to import while it is cheap because if you remember, I showed that criticality curve and how it impacts the cost, right? So while it is at a cheaper price, it's better to import and save their resources. And then when prices go up, it's a game, trade game between countries. And they're smart enough to conserve their resources and import. Similarly, they're looking at it in terms of water. A lot of water intensive products are being imported. Whereas countries like India and Asia, we're just looking at the returns in terms of money and not in terms of the loss of water. Okay. So a nation's water budget should also include these kind of import and export of products and how much of water goes into it. So most of if we look at India, the national water footprint of a production is larger than the consumption because of the export we are doing, right? So at a global level, this shows the flow of virtual water. This is only on agricultural trade. If you look at what flows from where to where, right? I'll give you a minute to look at this picture. So the arrows show about 10 gigacubic meter per year of water flows from one country to the other. Okay, well, it's all greater than. The lesser ones are not shown in this picture. So these are the big uh, chunks of water which is moved from one continent to the other through the agricultural trade. Right? So the green shows water import, virtual water import, and the red shows the export. From minus, you can see the legend, it goes up to the red ones are where they are exporting. So this is another interesting graph which shows what is the water footprint of different countries. Right? So if you see the global average water footprint is marked here around 1,200, and the domestic water consumption, the industrial goods water consumption, and the agricultural good water consumption together are shown in the bars. And yeah, so the water footprint of US is on the higher side of the chart here, and India and China are still much less. But what is the catch here?
Population.
Yes, so this is per capita. So if you look, multiply with our population, our total water footprint will be much higher. Per capita is much lower. Okay, so when countries need to look at these numbers, and also they should be looking at their water resources. That is when they can make a decision. This is the water footprint in terms of production and of different resources, including agriculture. And then what is the resources? If you match these two, then you can come up with the right decisions can be made when you're looking at your consumption and your available resources. Okay? And then what to export and what to import. So there is a lot of information. I think I will not go over the entire presentation with you. You can look at it. I'll share the link with you, and then this is about businesses. We'll be talking about it in my next presentation also, so I won't go through this whole thing. So businesses, just like what we did for embodied energy and circular economy discussions, we have to look at the entire supply chain instead of just looking at their own consumption, right? What is the water consumption in across the entire supply chain? Okay, and how where we have not talked about the gray water footprint a lot here. So it is very important to look at what is the gray water footprint of the supply chain also when it comes to a manufacturer. Okay. So when the consumer, if you're going to drink a cup of coffee, it's not just that, but the entire supply chain, how much of water was used and how much of pollution happened because of the water use. All that needs to be accounted for. Okay, so businesses traditionally, they only look at what happens in their industry. And the regulators also, like Pollution Control Board, they look at how much water was used by the industry and how much water they discharge, what is the quality of the water they discharge, and regulations are only centered around that. So can we improve in terms of water consumption? There are a lot of things we can improve, not just the water quality management, but even from the consumption point of view. Okay, how much of water was consumed and how effectively it was utilized in the manufacturing process also plays a role when you're looking at reducing the water footprint. Okay, so different as you go back in the supply chain, everybody has an individual role to play, and collectively we have to reduce the water footprint, right? From the food processor to the retailer to the farmer. Okay, so the total water footprint of the business, again, if you sum up everything, you can come up with the total water footprint, or the operational water footprint for the business and the supply chain water footprint. Okay. So there are a lot of industries which not just use water for making the product, but there can be a lot of the quality can be impacted not just by the chemicals or the other raw materials which went into it, but also for the cooling processes. There is a lot of water consumption, right? So if you look at thermal power plants, that is the biggest consumption of water, right? Even in an iron and steel plant, they use a lot of water. It may be surprising for you. How does an iron and steel plant it's just going to have the materials? It uses a lot of water for quenching operations of the coke, okay, and the steel. So that's also accounts for in the water footprint of the iron or the steel which comes out of it. So we have to make sure that everything is accounted for. And yeah, this will be another slide I'll be talking later. It's you can't look at things in isolation, right? So there's water footprint and there is carbon footprint, about which we already talked about. And these two are very closely connected, right? In various ways. I'll give you various examples on how emissions are connected to water. So if you're going to reduce water, and let us say we're all environmental engineers. So there is treatment happening. There is a treatment plant. We all know that even for the basic biological treatment, what is required? Biological activated sludge process. What is the biggest consumption in a treatment plant? The biggest energy guzzler, right? So if you increase your pollution load or your water, if you're going to use a lot of water, you're not mindful of the water input, there's a lot of wastewater generated, and then that's going to have a lot of impact on the carbon footprint when you're trying to treat this wastewater, right? We talked about zero liquid discharge plants. That has a huge impact on the carbon, the energy consumption, right? So whatever decisions we made, we can't look at things in isolation, right? So both have a very, very close connection. Solar panels, right, which is made for energy consumption, for making renewable energy. That also has a water consumption, right? You need to periodically clean the solar panels, and that's a water consumption. So when you're creating a product for energy, there is a water footprint. And when you're creating like products using water, there is a energy consumption. So again, life cycle assessment has to incorporate these kind of, already we are accounting for as water usage, but larger decisions, like I said, where to source it from, where to source the raw materials, we look at distances and transport, right? In the LCA, how far your raw materials come in, right? To only looking at the energy and the embodied energy and the emissions, we make decisions. But are we making decisions on how much of this raw material is using less water? What is the footprint of that raw material with respect to water? Right? So that also has to be embedded when we are making choices. It's an integral part of the LCA, but we need to give more focus on the water. Okay. So I think the rest of it is probably related to your LCA, which already we have discussed. What are the different phases? I will stop here and I will ask Bindu to show some of the problems which we wanted to uh, discuss with you. And using some of the concepts what you just learned, you can actually solve the problems. They're simple problems. She has provided links where you can get the data. Yeah, it's not just the products, our digital footprint also incurs water. That is an interesting problem there. We have a problem on coffee, how importing coffee bean from a different country. What is the water footprint of using our own coffee versus coffee from Brazil? The fourth one is quite interesting. With a lot of push given for millets these days as replacing rice and wheat. I hope all of you know that millets are mostly rain-fed. It has only a green water footprint, and that is also very small compared to rice or paddy cultivation, which requires like submerged water for like several weeks together. There's a lot of evaporative losses when you're growing rice compared to millets. And also millets are pest resistant, right, compared to rice, which needs a lot of pesticide at different stages, needs a lot of fertilizer input. So in multiple ways, millets have a low impact on the planet compared to rice or wheat. So it's not only healthy to our body, it is healthy to the planet to switch to millet. Where does our rice go? I think you'll get all the information if you're Googling. From where to where? Punjab, Andhra, West Bengal. So much of our river basins. We are having a huge water footprint for exporting the rice. This is a very interesting problem that I'm talking about in my next presentation also. The new and emerging demands on our water resources. Again, policies and decisions taken, as I told you, it's temporarily varying and also spatially. So this is one, as technology changes are happening, there is pressure on our water. We wouldn't have imagined data centers having an impact on our water resources, but of course, it's huge impact. It comes in terms of they don't consume water directly, but for their cooling purposes. Huge amount of water is used for data centers. And Google has recently signed a contract with the Andhra Pradesh, government of Andhra Pradesh, Chandrababu Naidu, chief minister, is well known for all his technology led growth. So, but unfortunately, location is very important when you decide on any industry, even textile and other places. They're wrongly placed um, in places where there is less water. Similarly, here in Vizag, where already there is a huge agrarian demand and we have water shortages, these data centers are going to have more impact on the nature because of the demand it is going to pose on the fresh water. So it will be interesting to see the numbers coming out of this problem. So we won't go into agricultural sector. It's a big, although it's the biggest water guzzler, there are a lot of other things which come into play when you want to make some water use efficiency in agriculture. No? The government policies, the farmers, their practices of But since it is the biggest consumer of water, even a small positive change will go a long way in agricultural sector. But as environmental engineers, we don't have a much role to play in that sector. The industry and the water supply sanitation, we have a larger role to play. So I thought I'll show you some numbers and some of our experiences working in industry and sanitation sector. Um, yeah. So water sector, yeah, in India is not in a good shape when it comes to water. We have been water stressed and we are actually going into water scarcity. This was even 2019. Now it is even much worse. Um, and our overall demand, 1,500 billion cubic meter is the prediction. And of which the industrial demand is about 56 in 2010, and they're expecting it to grow to 151, threefold increase by 2050. We are almost two-thirds of that now. And yeah, in industries, wastewater management is a huge challenge apart from the water consumption, which we talked about previously. So most of the time, uh, traditionally, or even now, sometimes, or in some places, we see disposal, direct disposal in water bodies. And ocean is a big receiver of all the pollution. Eventually, everything ends up in the ocean. Um, and very soon, we are going to have a lot of impact, visible impact also. Right now, visible impact is seen in all our inland water bodies. Many of our rivers and lakes are polluted visibly. But other things, what industry has been not been doing the right thing is on land disposal. Many, for a long time that was acceptable. I think everybody does the same mistake world over. When the regulations, when the impact is seen, only then regulations come in, and then they try to make changes. So land disposal was being practiced. We have seen this in several industries across the country. Every industrial site has a legacy waste, just like how we saw in Kodungayur, the large dump site. Every industry has a legacy waste disposal site, and nothing much is being done. Although government now is looking at the urban waste disposal sites. Every industry, since it is within their own premises, not much is being done. Right? We were investigating a few. I can show some examples from there. Okay, and slowly it became the water coming from the effluent was used for agricultural use. We have a huge agricultural water demand, and we don't have enough water, and it is not equitably distributed. So in the vicinity of the industry, if there are agricultural lands, the farmers were gladly taking that water for their land because they didn't have any other water for irrigating their land. Okay, so that was also, and it is also in practice even now in some of the water scarce regions, which is again a serious thing to look at because of the soil accumulation of pollutants in the soil and biomagnification in the crop and food chain and all that. Right? So treatment and reuse. Eventually, the stringent norms brought treatment into the picture, and industries were asked to reuse the water in the industry, which is a positive thing which is happening in some industries. Treatment and reuse in other industries also has happened. One example is the paper industry, the sugarcane industry, and the paper industry coexist next to each other so that the bagasse from the paper industry can go as that also the alcohol industries, the distilleries, they all take a waste from one industry and use it for their as a raw material in their industry. A lot of fermentation processes makes the sugarcane bagasse, to make other products like alcohols. Okay. So there is also that practice going on in India, and then comes the zero liquid discharge for the high polluting industries to control these discharge of water. The industry, the regulators came up with zero liquid discharge norm. That means no liquid should be discharged, uh, which is an extreme thing to do, but it is being enforced in some states. So I just wanted to show some interesting projects where I was involved, where we were investigating industries. Nagarjuna Agrichem, this is based in Srikakulam in Andhra Pradesh, where Google's data center is coming up close to that. This is a agrichem industry, which is in other words is a pesticide industry. They kind of give a nice name, agrichem. And there was, when we visited the industry, they wanted us to, under the pollution control board's pressure, they came to us to investigate what is the quality of their groundwater. So we found that while digging out a lot of information, that there was a huge fire in 10 years ago, and a lot of these solvents which were stored for pesticide making. There was a huge spill of solvents from these industries. And also we found these ponds, which is very, very typical of any industry. They have large tracts of land and they have these disposal ponds where their effluents were disposed of, allowed to percolate without any treatment. And for a long time they were using it. Now they have some treatment being done, but this was the norm. When we visited the industry, we sampled in so many locations within the industrial premises, and the ponds, we picked up samples from the ponds, and we found high levels of chlorinated solvents. If you, some of you may or may not know, chlorinated solvents are the most toxic among the solvents, and the number of chlorines increase, the toxicity level increases. So we found high levels of dichloromethane, dichloropropane, monochlorobenzene, dichlorobenzene everywhere in all the soil at different depths, the pond, the groundwater, everywhere. And there were complaints. The reason why they were asked to do this study is that there were a lot of people about 4 to 5 kilometer radius uh, who could feel something was wrong in their groundwater, right? So the investigation showed this is the predominant direction of groundwater flow, and we found chlorobenzenes in all these. These are, each one is a village, and this is the groundwater for the village water supply and also for agriculture. They were in excess, 100 times in excess of the permissible concentration of dichloromethane. We use that as a signature compound. So the impact for more than 10, 20 years is still felt in these villages. And then we came up with a lot of solutions for treating this groundwater, but I don't think it was implemented. It's quite an expensive affair to do groundwater treatment. So I'm not sure what was the outcome of the report we submit. So here, paper and pulp industry, again, in the same Andhra Pradesh industrial area. So we found that when we tracked the pipelines coming out of the industry, it went into the Krishna River, but they didn't discharge it in Krishna River, but there was an island in the middle of Krishna River. It came all the way into the island and they discharged it in the island, thinking that nothing is going to go into the river, it's only a land discharge, right? Or even the regulators are not aware that it has come this far into an island in the middle of Krishna River. So There are a lot of practices like this, which is ongoing in some cases, um, which is very sad because it is the people who are impacted far away, even far away from the industry, who bear the brunt of the pollution load. Right. So, Punjab, we all know uh, Punjab is agricultural, predominantly agriculture, and they have like very large fields, and also they have a lot of industries um, in certain pockets of Punjab where industrial water has been used for agriculture. This is one place in Punjab where there was a woolen and polyester was used for the manufacturing of clothing. So here they use a lot of dyes and chemicals to dye the polyester. It doesn't dye as well as cotton. So there is a lot of chemical usage. The region called Malwa, which is also like the cancer capital of, they say there's a cancer train, they say, which runs, uh, which carries people from one region of industrial area to a hospital. Uh, so there's a lot of impact. We were asked to study if it is okay. Now they had treatment plants and they wanted to see if the treated water was okay for irrigation. So we did a lot of studies. Uh, we grew. You saw me doing the harvesting, right? That's me. So we grew paddy and wheat in 2 seasons in the industrial premises where we used a farmer to do the same practices. And at the end of the growth season, we harvested. And so different plots of land were using clean water, industrial effluent, a mix of industrial effluent, treated effluent. So we had different plots, and we harvested. We did a lot of infiltration studies to see how the water percolates, how far it can percolate, and infiltration rate, and all that. We tested the soil, we tested the effluent from the treatment plant. Then we brought back the crop, the plant, the wheat and the rice plant, dissected and found this is a harvested plant. So packing it for bringing it to IIT. So we found chromium, which is used a major dyeing, one of the dyeing chemicals. Chromium was there, hexavalent chromium, and we found it everywhere in the roots, in the stem, in the grains, in the soil. So we had to give a report which the industry did not like. The treatment is not effective and they have to go for better treatment if they want to, and it cannot be used for food crops. You can use it for like bamboo or other crops which is not used for consumption of for people or cattle, right? So every time we go and give a report, we often the industry doesn't like it. The pollution control board takes it, but there's no action, unfortunately. So I can tell lots and lots of stories like this. We have visited several sites and done investigations like this uh, and documented the status. Okay. So, yeah, uh, in terms of pollution, yeah, it's prevalent, so prevalent. Just wanted to again bring our attention back on the quantity of water. Both have to be looked at from the point of view of water footprint. So if you look at the big picture, where does all our water go? Within the industrial use, it may be surprising to many of you to see that 87% of the water used in the industry goes to the thermal power plant. Right? This is a direct link to our energy footprint or the carbon footprint. Right? So that's again a direct linkage. So where do thermal power plants use water? When you look at the whole life cycle, you have to look at the end of life also. So it is ash, converted to ash. And managing this ash is a huge problem. I think Professor Su's presentation on energy, she was talking about how the quality of the coal in India is not so good. We have a higher percentage of ash content. So that much of ash, it's huge amount of ash which is has to be managed. And usually ash is made into a slurry, and that needs a lot of water, right? It's made into a slurry. It is piped, sent in pipes to ash ponds. Okay, usually there's no place. You need a large area for an ash pond, just like a landfill site. That much of ash is being produced every day, right? Some of it is sent for reuse purposes, for bricks and other things, but the demand and supply doesn't match, and a large amount of ash goes into ash ponds. So they have to transport it through pipelines in a slurry to the ash pond locations. Okay, so that needs a lot of water, right? And it evaporates in the ponds, and then there's a loss of water. So there's a continuous flow of water. So thermal power plants, yeah, cooling is a big thing. And then comes the ash, the boiler blowdowns and all that. So the rest of them, although it's a small percentage in terms of volumes, it is huge. Textile, iron and steel, here, these four are the major industries which are consuming water in India, high volumes of water. Thermal power plants, pulp and paper, textile, and iron and steel, right? So, um, so water use efficiency. If you're going to want to make big changes, you need to focus on these four sectors. Well, pay a little more attention on these sectors. So, industry has been uh, trying to achieve water use efficiency. Yeah, but the data says that Indian industries have still a long way to go in terms of water use efficiency. How much water used per ton of product, right? It's compared to other countries, it is very low water use efficiency. There is a scope to improve. Just like energy and water, you can draw a lot of parallels. Instead of looking at end of the pipe, treating the wastewater, we can look at the water use efficiency, okay, to cut down the water intake. And it will also reduce the load on the at the end of the life. Okay, so India's plans to cut down to optimize the water use efficiency by 20% in the coming years. So thermal power plant, where all water is used, just to show you what happens. So the biggest water use is, as I told you, in the cooling tower. Okay, and what can we do differently to reduce or increase the water use efficiency? Can we reuse? Same, your circular economy, we drew these circles, right? Reuse, recycle, refurbish, the circle gets bigger and bigger. So as much as possible, if we can use the water, try to make the water loop within the industry, the energy required for making better water use efficiency reduces, right? So you don't have to transport it elsewhere and treat it elsewhere, but as much as possible, loop it here. Similarly, so closed water recirculation, right? By using cooling water too, and the makeup water, raw water, uh, just by increasing, adding makeup water, but most of the water being reused in a closed loop system. Okay, so that is one way to reduce water consumption. And even in the ash handling and the coal handling, can we collect the water, the evaporative losses in an ash dike? Can it be covered so that you can recover the water which is evaporated to reuse it for coal handling and ash handling? A lot of steps are being initiated. And recently, TERI, the Energy Research Institute, has been coming up with a lot of recommendations for what interventions can be done. Again, drawing parallel to the energy audit presentation which was done, there can be short-term interventions and long-term interventions. Short-term with a lower cost, with smaller benefits, immediate benefits. Long-term, much higher cost, but better in terms of the return of investments. So recirculation. 70% of the water in ash handling system. In Chennai, particularly thermal power plants, there has been a huge pollution of the river because from the thermal power plant, which is on the east of the river, close to the ocean, they need to be close to the ocean because they have to discharge this hot water into the ocean, right? Uh, but then they can't have the ash ponds closer to the ocean. So they take it on a pipeline across the Buckingham Canal, across the huge river, which is in the north of the Chennai, and then take it to an ash pond. And over the years, they have been mishandling. There are leaks in the pipeline. I have personally seen sprays of ash slurry coming out of these pipelines and falling into the river and the Buckingham Canal. And so, tremendous impact on the environment in that area. The air is polluted, water bodies are polluted. The Buckingham Canal, when we did some core samples, the sediment, we found about 4 feet of ash uh, in the canal because of the continuous loss of ash during the transport. So a lot can be done in terms of housekeeping and making simple steps in the short term. And long term, they can switch from wet ash handling to dry ash handling, conventional wet cooling to dry cooling with a lot of investment. Uh, but we can bring these numbers down. Water use efficiency can be increased tremendously from 6.5 cubic meter per megawatt to 1.9 cubic meter of megawatt. There will be, it's not just cost to the industry, but it has also been calculated that the monetary benefit um, is also quite huge if they are going to invest now. And in terms of water savings, there's going to be a huge impact in thermal power plants. So yeah, every industry, this is something, a water audit, what we talked about, right, earlier. If there is a water audit done, then they can come up with these short-term, long-term interventions. The cost it will take is important. And then what is the return you're going to get? Okay. So paper and pulp, again, as I told you in my presentation, we have in recycling paper, India has been like really doing well. That's one success story we can talk about. Lot of water use happens in paper and pulp. You know that wood, again, it has a high lignin content and a lot of chemicals used for processing wood and making pulp. Okay, and so the chemicals can be recovered and the water can be again treated and reused. And then comes once the pulp is got, bleaching is done. Again, there's a lot of chemical use during bleaching. And finally, the paper is made. And so there's a lot of water use in both the two different phases of paper manufacture. So when we did the LCA and the eco audit, we talked about recycling, right? Aluminum, if you're going to use recycled aluminum, how much of embodied energy is saved? Same thing happens here. So, so much of water is used in the making of the pulp from raw wood. So when you're going to recycle, it is going to come right here, right? All your recycled pulp from the used paper you're going to skip the entire first phase because you get pulp. Okay. And so there's a lot of water savings also when you're going to recycle, right? So if we have that inventory, we can do a very similar comparison like what we did for how much embodied energy is recovered when you're doing recycled material. Similarly, we can do it for water. Okay, so so the numbers are here. If you're going to start from a wood-based paper industry, you need about 50 to 75 meter cube of water per ton of paper produced. Whereas if you're going to be using recycled fiber, or if you're going to reuse paper, then it comes down to tremendously by 1/5, 1/3 of water consumption per ton, right? And in India, as I told you, made a big progress in the 80s because our paper recycling is a well-established network. In 80s, it was 84% paper was made from wood, and recycled fiber was only about 7%, whereas now in 2024, it's completely reversed. 73% of the paper produced is from recycled fiber-based mills, while 18% is produced from wood-based, and the remaining is from like agro industries waste is also being used for making paper. Yeah, and short term, long term, there are a lot of strategies which the report has discussed about the paper mills, what kind of technology they can use to reduce the water consumption, and also in terms of the water treatment. Can we do a better job so that you get high quality water for reusing it in the same industry? That's the most ideal scenario. So you have a lot of water savings within the compound of the industry, right? So payback period is pretty good, less than 2 years in a wood-based paper mill and 8 years for recycled fiber-based paper. Right? So some more data on what is possible for the major water wrestling industries. So if this is the existing water consumption, and if you're going to implement the interventions short and long term, like the one suggested, we can drastically reduce the water consumption of each of these industries. Textile is another story where we were directly involved to make a change. We're yet to see the results in the full-scale plant. I'll share some of the interventions we have suggested in a short while. Yeah, so all of these are going to have there is return of investment is huge, not only in monetarily, but also in terms of the impact on the planet. If you're going to do an LCA before and after the intervention, that will be a huge impact on all the parameters, all the impact assessment parameters. Okay. So yeah, it's not enough if we are just going to do some short-term, long-term interventions in terms of technology, the engineers are doing stuff on ground, but a lot has to be done at the policy level to make all that effective and implemented. So right from location of industry based on water availability rather than other factors, right? Most of the time, land availability is discussed. Whichever state offers to give land, lease the land, the industry just goes there, right? Most of the time, that is what decides, or tariffs. But unfortunately, water is not in the picture because they think they can get water from wherever. They either dig deeper or transport via lorries. No, this is what to say, very, very sad to say that that is not at all factored. The carbon footprint of transporting water or the eco footprint of drilling deeper into the fossil groundwater is not at all considered in making decision. Right? So recently, the Bureau of Water Use Efficiency has been set up. which is trying to come up with some benchmarks for water use for different categories of industries. And industries will be able to measure up where they are and try to aspire to reduce their water use efficiency, increase their water use efficiency. Okay, and yeah, water audit is instead of making it optional for the industry, even energy audit, what we heard was industry is doing it. There's no mandatory thing that they have to do it. But if we make all this mandatory, and when the industry goes for its license, every 2 years they go for a consent to operate. If they go with these audits and their water use efficiency numbers, energy use efficiency numbers, that I think will be make a great change. And make it transparent. Most of the time, the industry data is not so transparent. If it is transparent for the government and the public to view, like in a dashboard, I think right things will be done in the industry, right? And pricing tariff plays a very, very important role. That is where the government, I can give you one example. The Chennai Petrochemicals Limited, the refineries, way back in early 80s, there was a huge water shortage in the Chennai, and the government decided to increase the tariff for the industry because they cannot do it for the common people. They increased the water tariff 3 times for the industry. And that made a huge change. In some industries paid, but then some of the big industries like the refinery of Chennai, which is also a big water guzzler, they decided to look at it differently. They did all the math and they decided to take wastewater. They told the Chennai the government that I don't need your water, give me your wastewater. That was like a big out of the box thinking at that point of time, right? Almost 40 years ago. So and they were glad enough to give their wastewater because it reduces the burden on the treatment plants, the wastewater treatment plants. So they gave the wastewater free of cost to the industry. And the industry put up its own treatment plant and they treated it even through RO because the quality of water required for the industry was almost like RO water quality. So it went all the way biological of ASP, settling tanks, then they went for RO. And in spite of all those investments, they were able to uh, get a better deal than buying the water from the government. That was the first example, I think, across the world to use wastewater for industrial process because of that one decision the government took, right? So recently, now they have developed another model where the government, they found this to be more profit making. Now the government is investing on wastewater treatment plant, the tertiary treatment. This is called tertiary treated with RO. All our wastewater treatment, at least 2 of our wastewater treatment plants have this RO at the end of the wastewater treatment, right? I think I don't see this model anywhere in the world where the city wastewater is going for an RO. We have seen RO for water desalination and supplied as drinking water, but here they use RO for treating the wastewater and supplying it to the nearby industrial parks. So that was it worked out. Economics worked out, the business model worked out, and now the city is treating water and supplying to industry. Right? So these are great examples how tariff, how can play a role in cleaning up the environment and also reducing the water consumption. Also, I think the government can incentivize industries who have gone for ZLD and doing a good job because they're incurring a lot of operational expenses. So incentives can be, and of course, R&D and innovations are required, because we need to constantly improvise the way we use water, the manufacturing side, the way we treat water downstream. Okay, innovations are required and it is happening. Right. So one example I wanted to show is what we have done. The electrochemical processes are quite well developed in our lab. We have used it for multiple systems like chromium, dyes, pharma industries, and we extended this with the help of our funding from Indo-German Research Center. We have a pilot plant now operating in Tirupur, the textile hub in one of the textile industries treatment plant. So this is a pilot plant running there, successfully treating the dye effluent without any chlorine. Right now, they are just using chlorine, which has a high impact on the effluent. It reduces the color, but it imparts the disinfectant byproducts in the water when you use chlorine, and organics are there. So we have this is a flow diagram of the effluent coming from a textile industry, where they mix the dye bath and the wash water, which is 80% and 20%, and the volume increases. And the whole thing goes for biological treatment, followed by hypo treatment, is where they dump chlorine, and then they go for multiple stage RO. Everywhere there is sludge produced, a bio sludge produced, there is a lime sludge produced. There is a lot of energy requirement in the RO. So it is a cascading effect, impact on resources. They use a lot of resins, they use membranes. So there's a lot for the entire water to be going through the RO. And then comes the evaporation. And because it's a ZLD, they have to make it ZLD. They evaporate the reject water, which is another energy guzzling unit. Okay, evaporators are used, and some water is recovered. The permeate is, they're able to reuse it in the industry itself, which is a good thing. But there is a lot of salt produced by evaporating the reject water. And this salt is highly toxic because of all the chemicals they have used previously, including all the disinfection byproducts, chlorinated compounds sitting in the salt along with the dyes, and you cannot use it. And it has to be disposed in a hazardous waste facility, which is again, it has to travel like 300 kilometers to come into a facility and dump there. Right? So there's a lot of footprint, there's a lot of chemical footprint. So whereas if we replace this, our idea, yes, Sue, I can answer. Take your question now.
So I'm wondering why they initially mixed the dye bath and the wash water, because I can imagine that the wash water is a lot cleaner than the dye bath. And so basically, you're taking something that's already you're making that wash water and making it a lot more polluted. And so if you just kept those two streams together, you might have a lot less really polluted water in the dye bath, and the wash water would be easier to treat.
Yes, you're right. That's in fact one of the suggestions we have given them, but they have been doing this because they are going for biological process first. And when the dye bath is concentrated, they're not, the microbial processes are not going to work. So they just found it easier to just mix them all up and send it to their biological process, which is another issue here is now the textile industry, in the manufacturing side, they have gone for high-end dyeing units, which is all automated, computer controlled systems where the sequence of processes happen in the same unit. So initial washing, then initial processing with chemicals, and then the dyeing. There are like 4 or 5 processes which happens in one unit, which is automated. And so all these processes send out the waste together. So, but that also they can automate. That's what we are telling them. If you can have a diversion automated, after the dyeing, you can divert it and then you can use the remaining processes collected separately. So that's one suggestion we are trying to give them to also make the processes, the electrochemical ozone oxidation process, which we have developed in the lab and it was working effectively. We are trying to tell them that use it for the 20% dye bath, concentrated colored water, and the rest of the wash water doesn't even have to go through an RO, because dye bath is the one where they add a lot of salt. That's the problem. When there is high salt and highly toxic dyes, the microbes don't work. So they mix it up and send it to the microbiological tank. Whereas if they can separate it, then all this can just go through a regular conventional biological treatment process. Whereas 20% alone, they can focus on electrochemical oxidation process, which is going to be energy intensive. Again, yeah, anything which is not chemical intensive has to break down in some other form. So it is energy intensive, but it doesn't leave a residue. There is no sludge. So it's very effective. And then we can go for the salt removal in the subsequent step. For a small salt removal, again, we need to depend on RO. So, but the RO is restricted to just 20% of the water, and so it's 80% energy savings compared to the previous option. So this is what we have demonstrated in the industry, and there is a lot of hesitation because they've already invested on the RO for the entire plant, and they've been doing it that way. And any shift, behavioral change needs a lot of other factors to coerce them into it, like regulations, or we need to show them the money, and we're trying to work out the money part by make them adopt this practice. They only look at the energy cost for the for our process, uh, which is prohibitive according to them. It's huge energy cost for us, but we have to wait and see. We're trying to push, and we're trying to go to new industries who have not yet invested. Like Tamil Nadu already said zero liquid discharge is mandatory and they've invested. So it's very difficult to make them change. So we're trying to work with people like Rajasthan and other places, Punjab, where they have not yet installed. They have been like evading the government for the zero liquid discharge. And as I told you, they were sending it to the fields for irrigation when we did the study. So we are trying to work with them because they are going to invest, and we can invest on a better system like this, where we are getting very good efficiency. Yeah, in terms of cost, we are trying to cut down on the ozonation, and we are a lot of things we are still continuing the R&D so that the cost doesn't become too prohibitive. So although the cost currently is this much, and our cost is about 85 kiloliters, we are trying to see, we are changing the electrode so that the energy consumption goes down. They have to, I mean, right now, funding agency, but I think the positive things, and they to make things better. The things we are currently trying to change it to boron doped electrode, diamond electrode, which is a large initial. Then the energy efficiency. renewable energy can be used to cut down the residual COD can adsorption rather than going all the way to cut down to reduce the COD. Yeah, so I think we're almost at 4, so I wrap up. Examples demonstrate isolation, right? Lot of the studies mostly focused on energy, greenhouse gas emission. And the water, looking only at water. The whole concept of zero liquid discharge, if they had looked at things, right? So since the energy cost is going, example, for evaporation, these textile industries are using biomass so that co-processing for producing energy so that they can these evaporators, which has another biomass. There's a lot of emissions associated with that. So cut cost, meet the regulation. Instead, they can on doing the right thing and energy water nexus, and we have to look at balanced manner. Energy when it comes where we talked about water in the earlier presentation, just decision making on different food. Energy in India, the policy for running their diesel power, that is from a social point, farmers are getting benefit. People just switch on their and just come away from home, since it's energy is on, and then they come back home and no water is just pumped out field and goes out, and it's such a huge waste. And what so policies have to look behavioral aspects of people. Subsidies everywhere, fertilizer subsidies are people are not interested in going for organic. Are interrelated: food, water, energy. Looked at and waste. I can add another. When you're looking at food, water, energy, you should not forget, right? People, you can't put technology, use a lot of waste and forget about salt in the textile industry or the sludge, right? Nobody worries about the sludge. Even the biogas plant, what we visited the other day, focused on bottling the gas and selling it, focusing on the volumes of being generated in the middle of the city. There's no farm to use it. So much nutrient. So it's like all interconnected, right? So holistic thinking is important. And set up some slide to show. We talked about problem. The new demands on water is coming up every day. Water consumption required for data centers. And yeah, 8,000 terawatt China currently, and 200 huge water per year of water is required just for cooling. Climate conscious cooling. I think China has found a way having a data center in the ocean, which can take care of their cooling, right? And out of the box. I'm also worried about the next big India is set to too long from US and other countries. And again, that's a huge guzzler. When I was doing my postdoc research, silicon wafer chips and all our experiments were in this small 1 centimeter, which we used to etch, and we were using so much of solvent of water, high quality water, ultra high purity water. It's not even just RO. You have to go one more level of membrane processes to get that water to clean the small chip. Now imagine manufacturing semiconductors, lots and lots of these chips. I don't know. It's mind-boggling to even think where are we going to get the water. And India has accepted to expand their start their fab industry and expand it. So there's a lot of solvents also going into manufacturing. It creates a pollution load. So it's something we hope the government thinks about instead of an afterthought after the pollution happens, and how do we remediate, which is even much bigger, has a much bigger cost and footprint. Right? So those are some of the thoughts I want to leave you with today. How water has an impact, and how ignoring the of your life cycle assessment. Consider the economics, otherwise it's not going to be accepted, like the textile industry. It also has to be socially acceptable. Like farmers, it's very difficult to make them switch because they are used to growing rice and paddy. They switched easily from millets few decades ago because rice and wheat was more like a cash crop. They were yielding more. So, but yeah, so society working with people is the most difficult thing to do. But I feel like money can play a role. Whenever there is a profit, people will switch to it. They don't need to go through behavioral change sessions, right? So that's where I feel startups and new ideas play a big role. If we can come up with solutions which are also cost effective, then the switch will be automatically made, whether it is industry or people or government. But that's the ideal solution. Good for the environment, low cost, low energy, low impact, right? That's like an utopian, sounds like an utopian thing, but we can make it possible with so much of bright young mind. That's what will give us a true solution.